So, let us look at a few characteristics of this electric motor powertrain which have made them also attractive from the perspective of powertrain applications. Okay. So, if you look at the broad characteristics of an electric motor, and please note that like in an IC engine powertrain, the energy system should also provide like energy for, let us say the air conditioning system, like, and it should drive the AC car AC, and then like it should also be providing power to the, let us say, power steering system. If you have an electric power steering, the energy source should provide the energy to drive all those systems, right, or what we call as auxiliary devices. So, if you look at a typical electric motor, we can visualize the torque speed and power speed characteristics of an electric motor in this way. So, what happens in an electric motor is that like the torque delivered by the electric motor remains by and large constant till what is called as a base speed. So, let us call this as omega b. So, in this case, in this graph we are plotting the speed of the motor omega, the angular speed, versus the torque and the power. So, we can see that the motor delivers let us say a maximum torque T max till what is called as a base speed, and the power increases in this region, and then like it becomes a constant beyond the base speed. So, at the base, after the base speed, the power remains a constant, and then what happens to torque? P equals T times omega. So, or T becomes P by omega, right. So, if the power is constant, we can immediately see that the torque is going to go like a hyperbola, right, beyond the base speed. So, this is a very nice characteristic of an electric motor, right, is not it? Because when we discuss the requirements from a powertrain's perspective as regards to the characteristic of a prime mover, we wanted an ideal traction hyperbola. So, an electric motor beyond the base speed seems to have an ideal traction hyperbola. Okay, that is point number 1. Okay. So, we will see how this is going to affect our what to say design of the electric powertrain. So, ideally from this building on this discussion, we will see that if we are able to keep the base speed as small as possible, right, then the characteristics are going to go like a the torque speed characteristics are going to go like a hyperbola over an extended speed range, which is advantageous for it. But the question becomes, are there motors like which will provide a very narrow constant torque region, okay. So, and a much larger constant power region. So, those are some questions, okay, which we are going to revisit shortly. So, if we look at the electric motor characteristics, so we have what is called as the base speed, which we shall denote by omega b. So, it is the speed till which the motor delivers an almost constant torque. Okay. So, that is the definition of base speed. Then we have what is called as speed ratio. Speed ratio x is defined as the maximum speed of the motor to the base speed of the motor. Okay. So, that is this definition of speed ratio. Obviously, the value of speed ratio is greater than 1, right. So, it is the maximum motor speed divided by the base speed. So, a few points to note as far as the motor characteristics are concerned. Let us say we consider a fixed power rating, okay. So, essentially what we are going to denote as the P max is given to us, okay. So, consequently we can immediately observe that for a given P max, an increase in x, of course given P max and omega max, right. So, an increase in x, what will happen with an increase in x? If omega max is fixed, with increase in x, omega b will reduce. If omega b reduces means the point after which the power becomes constant is shifted to the left in this curve, right. So, essentially if we are reducing x, this point is going to be shifted to the left. So, an increase in x ensures a longer constant power region and consequently a higher motor maximum torque. Why? Because if we are writing P equals T omega at this base speed, what will happen? We will have P max to be equal to T max times omega b, right. So, if I am reducing omega b for the same P max, T max is going to increase. So, if we have a higher maximum motor torque, what will happen? This will imply better acceleration and gradability characteristics, is it not? Because gradability and acceleration are decided by the initial torque that we get out of the prime mover. So, essentially we are going to get better acceleration and gradability performance. Okay, so that is the advantage, but there is an, depending on the type of motor, there is an upper limit on the speed ratio of the motor. We can't keep on increasing the speed ratio. Yes, we can increase it numerically, but practically such motors should be available, right, to be used in vehicles. So, there is an upper limit on the value of x. Okay. Another feature which we would be observing due to this hyperbolic torque speed characteristics from an electric motor is that if you look at a typical electric vehicle, we may even have a single speed transmission, right. So, there may be only one gear ratio or sometimes there may be two gear ratios, right. So, the choice of the gear number of gear ratio is also decided by the corresponding motor's torque speed characteristics vis-a-vis the requirements from the vehicle performance perspective. But the main point to note is that the number of gears is certainly reduced, because the electric motor has a hyperbolic torque speed characteristics beyond the base speed. So, that is an advantage for us from a powertrain's perspective. So, we do not require as many gears as we required with an internal combustion engine driven powertrain. So, that is an important advantage of an electric powertrain. So, the choice of a single gear or multi-gear transmission depends on the torque omega characteristics of the motor. Okay, that is important. If a motor has a high value of x, that results in a longer constant power region, because if we decrease the value of x, omega b is going to be, if we increase the value of x, omega b is going to be reduced, right. Omega b reducing means, the base speed reducing means we are going to have a longer constant power region, okay. Then a single transmission may be sufficient. So, that is one important point to note. Okay. So, now let us consider a single speed transmission, and then we will just write down some quick write down some expressions quickly from what we have already learned before from powertrain's perspective, so that we get a picture of how we can get the initial powertrain ratings, you know, from the perspective of vehicle performance. So, let us first look at the what is the various requirements of a vehicle as far as powertrain is concerned, like maximum speed, gradability and acceleration, right. Before we go there, just one more point to note. Please note that the relationship, if I am considering a single speed gearbox, okay, with an electric vehicle, the relationship between T max, which is the maximum motor torque, and the corresponding maximum traction force, let us say we call it as F max, is F max is going to be equal to T max times Nt eta T by Rw, okay, where Nt is the transmission ratio, okay. Eta T, as we know, is the transmission efficiency, okay. So, these are expressions that we are already familiar with. So, the transmission is going to, transmission ratio is multiplied with the output of the motor, then multiplied by an efficiency term and divided by the wheel radius, right, to give the longitudinal force of the longitudinal force that is available from the powertrain to drive the vehicle, okay. So, now let us look at various performance requirements from the vehicle's perspective and see how we can obtain the ratings for the motor, right, based on what we have learned. So, maximum vehicle speed. So, recall that the maximum vehicle speed, maximum vehicle longitudinal speed V max, and the prime mover speed, in this case the prime mover is the electric motor, right. So, and the maximum speed, maximum motor speed, so I will not say recall, because we initially wrote down for an engine, so we did not write for a motor. So, let me write it as a statement. So, maximum motor speed omega max. So, the statement is the maximum vehicle longitudinal speed and the maximum motor speed are related through the following equation, which is very similar to what we wrote down when we did the analysis for the conventional IC engine powertrain, right. So, what is V max? Let us say omega max is the maximum motor speed, right. Omega max divided by Nt will give me the maximum wheels rotational speed, right, corresponding to omega max. Then if we multiply by Rw, that is going to give the corresponding circumferential speed at the wheel. Then we go and multiply by 1 minus lambda, where lambda is the wheel slip ratio, that will give us V. So, we can observe that this is something which we already derived when we discussed transmissions, right. So, the concept is the same, we are just applying for an electric motor, okay. So, this is the maximum longitudinal speed, the relationship between the maximum longitudinal speed and the corresponding motor maximum speed, right. So, now the corresponding power and torque requirements are the following. So, what are the corresponding power and torque requirements? So, if you look at the torque required to essentially satisfy this V max, what do you think are the vehicle loads that the powertrain has to overcome? we are cruising at maximum longitudinal speed, right. So, the main way on a flat road, assuming a flat road. So, the main resistances that the vehicle powertrain has to have to overcome are the rolling resistance and the aerodynamic drag, right. So, that is going to be half rho a CD AF V max squared, right. This will be the force or the load that the vehicle powertrain should overcome, multiplied by the wheel radius will be the torque at the wheels, then we divide by the transmission ratio and the transmission efficiency. So, this will tell us what will be the corresponding motor torque required. So, how did we get this? We just got it by here, right. So, essentially from this equation we can see that T max is going to be equal to F max times RW divided by NT eta T, that is it. Okay. So, what we did, we just substituted for F max. While going at maximum speed, you know, FRW and aerodynamic drag are the forces that we need to overcome. So, that is going to be the rating of the motor. Okay. So, then what will we get for power? Power required for V max will be this thing, the force that we need to overcome, right. This is the power rating of the motor divided by multiplied by V max, that will be the power required at the wheels, then we divide by the transmission efficiency, right. So, that will give us the corresponding motor rating, you know, which would essentially be required to drive the vehicle at this maximum speed, because what is this? F times V, F times V is the power, right. So, in the numerator, instead of writing torque times omega, I have just written F times V. So, and then divided by the efficiency term, and that will give us the power output. Okay. So, that is as far as maximum vehicle speed is concerned. So, then the second one is gradability. So, as we know, the gradability is indicator of the maximum slope that the vehicle can climb upon, right. Gradability is defined as tan theta S max. So, now similarly we can essentially write down the torque, motor torque required for satisfying gradability, right. What will that be? That will be grade resistance plus rolling resistance plus aerodynamic drag, which will be this. Okay. So, these are the forces that the vehicle powertrain needs to overcome. Then how do we get the torque, motor torque? We multiply it by the wheel radius, divide by the transmission ratio and the transmission efficiency. Then the corresponding power required would be what? Just the force that we wrote down above, right. The grade resistance plus the aerodynamic drag plus the rolling resistance, right. Then once again we multiply by the speed at which the vehicle is going on the grade divided by the transmission efficiency. So, okay. So, this is how we get the expression for gradability. Okay. So, then the last requirement that we will look at is acceleration performance. So, in electric powertrain we will see that one more advantage is that, like, we will be able to get an explicit relationship between the torque and power requirements to satisfy the acceleration performance. Okay. So, that is an advantage. We will see how we get a simple expression for this. Let us say we desire to go from a speed of 0 meters per second to Vf in a time interval of Tf seconds, let us say. Okay. So, that is our requirement, right. So, for acceleration. So, let us consider only inertia. Consider only inertia. for the time being. Of course, when we are accelerating, let us say we are accelerating on a flat road, inertia will be the dominant term, so that is why we are considering inertia. We will see what happens if we add the other terms like rolling resistance and aerodynamic drag shortly. Okay. So, let us consider inertia. By utilizing the Newton's second law of motion, we can obtain this following equation. So, where we are just integrating over the acceleration time to figure out what will be the torque and force requirement. Okay. So, because the force requirement f of t keeps on changing, right, and also please note that as the vehicle speed changes, the output from the prime mover also will change, right, because the torque will remain constant till base speed, after that it will fall hyperbolically, right. So, that is why I am writing f as a function of time. So, if we were to integrate this equation, so we will get Tf on the left hand side, then we will have m. This we are going to split into two regions. So, we will see that this force or torque, we can see that it is going to remain constant in the base speed region, then it is going to fall hyperbolically, and so there it will become a function of speed, right. So, using that fact, so we are going to see that this, so this is not Tf, this is Vf, sorry, okay, I am going to integrate from 0 to Vf on the right hand side, right. So, we will split into two regions, 0 to Vb and Vb to Vf. Of course, I am assuming that the final speed is more than the base speed, which is a reasonable assumption to make, right. So, integral 0 to Vb, so then it will become dV divided by, so here the force output that we will get is going to be P max Vb times eta t, because how did we get this? At the base speed, P max equals T max times omega b, or I can say F times V divided by eta t, right. So, I just essentially make use of that equation to get this expression. Then from Vb to Vf, we will have dV divided by P max by V. Now, you can see that this is a function of time, right. So, let me write it as P max by V times eta t. Okay. So, these will be the two parts. Okay. So, if we integrate, we are going to get m times Vb squared divided by P max times eta t plus m divided by P max eta t Vf squared minus Vb squared by 2. Okay. So, if we simplify this equation, we will observe that we are going to get P max equals m divided by 2 eta t Tf Vb squared plus Vf squared. So, we observe that we have got a simple expression that tells us what will be the motor rating to satisfy a given acceleration performance. Okay. So, let me write as P max to satisfy this acceleration requirement. Okay. So, the last part which I am going to essentially point out to you is that in this expression for P max, we are not considered rolling resistance and aerodynamic drag. So, if we want to get a first cut expression to include those, how do we do that? So, if aerodynamic drag and rolling resistance are considered, the corresponding additional power is the following. Additional power requirement is the following. So, P, let me put it as P additional, that is in addition to this P max what we derived here, right. So, that is why I am calling as additional. So, this is going to be 1 by Tf 0 to T FRW is the rolling resistance, and then half rho A CD AF V square, that is going to be the aerodynamic drag. So, what is within the square bracket is the net force that needs to be overcome, resistance needs to be overcome times V will give us the instantaneous power, then we integrate over the entire region of acceleration and we average it over the time. So, this is more like a time averaged quantity, right. So, this is how we will get it. Of course, here now we see that we need to substitute for V, right, because we are integrating over time, but V is also a variable, right. When we are accelerating, we are going to go from 0 to Vf. So, to get a first cut relationship, like what we do is that like we assume that the speed evolves with time in this manner, that is the speed is what to say V is going to be Vf times square root of t times t by Tf, okay, which is a reasonable assumption to make looking at typical vehicle time speed profiles during acceleration, okay. If we do this, then this implies that the additional power requirement is going to be equal to 1 by Tf integral 0 to t FRW Vf square root of t by Tf plus 1 by 2 rho A CD AF Vf cube t by Tf to the power 3 by 2 dt. Oops. Wait a minute, I think this parenthesis should come here, okay. So, this is the additional power that is required. So, if we do the integration, we will observe that this P additional is going to be equal to 2 by 3 FRW Vf plus 1 by 5 rho A CD AF Vf cube, okay. So, this is the additional power that needs to be provided by the powertrain in addition to overcome the inertia, right, if we consider rolling resistance and aerodynamic drag. So, what do these simple expressions provide us with? Okay, they provide us some tools, like to calculate the torque and the power requirements for satisfying these various vehicle performance requirements. So, on the the impact of these derivations is that if we are given some basic vehicle performance requirements, we could use these expressions to get the corresponding motor power rating. Obviously, depending on the type of vehicle and the type of operating conditions, then these numbers are going to have a relative variation, right. See, for example, if we are going to have a high performance car, the acceleration power may be significant, okay. So, we have to calculate these ratings and make a decision on what our final powertrain will be, so that we satisfy all the performance requirements, okay. So, that is the idea, okay. So, I will stop my discussion on this electric powertrain with this. I just wanted to give a broad overview of what an electric powertrain is, what are its various realizations and characteristics from the perspective of powertrain, and some simple analysis to supplement what we learnt in our conventional transmission analysis. That was the objective of this particular lecture, right. Thank you.